Hello, students. So today we will be talking about chapter 3, water and life. So as we can see, this topic deals with water. So we'll be talking about all the emergent properties of water and how water as a molecule is going to help living organisms to sustain life. So the molecule that supports all of life is water, and water makes life possible as it is the most common substance to exist in all three states of matter: solid, liquid, and gas or water vapor. Now, water possesses unique properties that helps living organisms to exist on Earth. And the structure of the water molecule allows it to interact with all other molecules. So we know that there are polar covalent bonds in water molecules, resulting in hydrogen bonding. Now, why was water called a highly polar molecule? Due to the unequal sharing or unequal distribution of electrons on both hydrogen atom and oxygen atom. So the electrons of the polar covalent bond are going to spend more time near the oxygen than the hydrogen because oxygen is partially electronegative. So the polarity of the water molecules helps to form the hydrogen bonds with each other. So we see here the hydrogen atoms have this partial positive charge and oxygen has a partial negative charge. And there are hydrogen bonds between the hydrogen atoms that is attached to oxygen, making it a water molecule. The four emergent properties of water once again help life to exist. So I've put here a learning objective. What are the properties of water? Water has four main properties that facilitates living organisms to survive in the environment. One, cohesive behavior. Water has the ability to moderate temperature. It can expand upon freezing, and it is a very versatile solvent. So let's look at each of these emergent properties. What then is cohesion? Cohesion is the phenomenon where hydrogen bonds hold the water molecules together. And it helps in the transport of water against gravity in plants. We can see here how, on account of cohesion, the roots of the plants, they're going to absorb water. And as the water is being transported to the stem, to the branches and the leaves, it's moving against gravity, and that's cohesion. Let's talk about what is adhesion. Adhesion is derived from the term to adhere, which means to stick. So adhesion is an attraction that exists between different substances. For example, between the water and the plant cell wall. So when you look at a surface section of a plant cell, these are two types of water conducting cells. Later on, we'll talk about phloem and xylem, which are water conducting cells. And that's the adhesion that is existing between the plant cell wall and water. So that's adhesion. What then is surface tension? Surface tension is a concept, which is a measure of how difficult it is to break the surface of water. And here, the classic example is a water strider. This is an insect which is walking on the surface of water. Now, what does it do when it walks on the surface of water? It creates this tension. So it breaks the surface of water, wherein the hydrogen bonds, there is surface tension due to the hydrogen bonds between the molecules of the air-water interface and the water below it. And that's how you can see the surface tension that it is creating while it is moving in water. And water has an unusually high surface tension because of this hydrogen bond present between water molecules. With respect to temperature and heat, the next emergent property, kinetic energy. We've learned what is kinetic energy? Energy in motion. And kinetic energy is associated with the random motion of molecules or atoms, which is then referred to as thermal energy. Thermal comes from the word temperature. So heat is thermal energy that is being transformed from one body of matter to another. And temperature is going to represent the average kinetic energy of the molecules in any form of matter, whether it's solid, liquid, or gas. So the next emergent property is the high specific heat of water. What then is specific heat of a substance? It's the amount of heat that has to be lost or absorbed by 1 gram of that particular substance in order to change the temperature by 1 degree Celsius. Must remember, take note of this fact. It would be asked in the exam. What is the specific heat of water? The specific heat of water is always 1 calorie per gram per degree Celsius. And water can resist changing its temperature because of the high specific heat. So water's high specific heat is now traced back to the hydrogen bonds that are present in the water molecule. Therefore, we've seen in chemical reactions that chemical bonds are broken down. For a bond to be broken down, and specifically hydrogen bonds break when heat is absorbed, and bonds are forming when heat will be released. And so take note of these highlighted or bolded words or terms. They are important for the exams. You will be asked questions on definitions, terminology, concepts. So what does this high specific heat of water do for a molecule? It is going to help to minimize temperature fluctuations so that life can be permitted on Earth. If the high specific heat of water did not minimize temperature fluctuations, then life would not be able to exist. Let's see, why does ice float on liquid water and it does not sink? So ice floats in liquid water because the hydrogen bonds in the ice molecule, they are more ordered, thereby making ice less dense than water. Now, water reaches its density, the greatest density at 4 degrees Celsius. So you could be asked a question, what is the density of water? The density of water is always 4 degrees Celsius. That's the highest density it can reach. So what would happen if ice sank? If ice sank, then all the bodies of water would eventually freeze and become solid, thereby making life impossible on Earth. So we see here, if you looked at ice, a solid state of water and matter, you see the hydrogen bonds are very ordered, they are very structured. In liquid water, the hydrogen bonds that are present, they can break easily. So you can see here that there is very little space between the hydrogen bonds. Here there is more space, showing you that hydrogen bonds can easily break and reform in liquid water. Now they're showing you a shrimp here. On the surface of the water, there is ice, but below the layer of ice, there is water, and the shrimp can swim in the water, in liquid water. Why? Because the hydrogen bonds in the water molecule can easily break and they can easily form. Whereas the hydrogen bonds in solid ice are very uniform, they're very structured, they're ordered, they're tightly packed. And so it would not be able to swim in the ice. Why is water referred to as the best solvent? What is called the best solvent? As it can dissolve almost all substances in it except the hydrophobic substances, which would be oil. So we come to terms that we normally use, basic terms in chemistry and biology called solute, solvent, and solution. And then we'll refer to what is an aqueous solution. So the way I define a solute is a solid substance that dissolves in a liquid. And in the next slide, I'm going to show you the classic example with each of these terms attached. Solvent is always the liquid that helps to dissolve the solid. And that liquid will always be water. Solution is a mixture, it's a homogeneous mixture of both solid and liquids. And now we come to the term aqueous solution. Aqueous is derived from the Latin word aqua, which means water. So aqueous solution is one in which water is the solvent. So let's take the classic example of you have a beaker of water. So water is your solvent, and you have table salt, which is sodium chloride dissolved in it. So the solid substance, which is table salt, is the solute. The liquid, which is water, is the solvent. And this homogeneous mixture of solid and liquid, the end result is salty water, would be referred to as the solution. So you have sodium and chlorine, which is sodium chloride, which is table salt. We saw in the previous chapter, ionic bonding, classic example, table salt. When you mix table salt, which is sodium chloride, in water, you get sodium ions and chloride ions. So Na plus Cl negative, sodium chloride, which is your solid. So water can also dissolve compounds which are made of non-ionic polar molecules. And every large polar molecule, even large polar molecules such as proteins, when you think of a protein is a large polar molecule, can also dissolve in water. Why? Because proteins are composed of amino acids. And we'll talk about amino acids, which is the polar molecule we call macromolecules or biological molecules in chapter 5, the macromolecule chapter, where proteins will dissociate into amino acids, into its two components. And so they can dissolve in water if they have ionic and polar regions. And amino acids, they have polar and ionic regions. So what then is a hydrophobic and a hydrophilic substance? Take note of these two terms because we will be requiring it in chapter 6 when we do tour of a cell. Our cell membranes are made up of a lipid bilayer. So extremely important terms for the whole semester to remember. They will recur again and again in the chapters to come. So let's define now what is a hydrophilic substance. Hydro is derived from the word water. Philic comes from the Greek word philos, which means love. So a hydrophilic substance is a substance that loves water. It has an affinity for water because it can dissolve in water. Therefore, into quotation marks, we call it a water-loving molecule. Let's go to the term hydrophobic. Hydro, again, derived from the word, which means water. Phobic in Greek comes from the Greek term phobia, which means fear. So a substance that does not dissolve in water, it does not have an affinity for water. Therefore, it's termed into quotation marks a water-fearing molecule. Oil molecules are hydrophobic because they do not dissolve in water. They have relatively non-polar bonds. Oils, lipids, and fats are all termed hydrophobic molecules. The hydrophilic ones will be all the molecules that dissolve or any substance that dissolves in water, has an affinity. Salt, sugars, we just saw. Proteins, which will split into amino acids, its components. They are all hydrophilic substances. And we see that hydrophobic and hydrophilic substances form the major ingredients of our cell membrane, the lipid bilayer model. Now we come to the acid and basic conditions. How are they affecting all of us, all living organisms? So the hydrogen atom in the hydrogen bond between two water molecules can shift or move from one atom to another. When the hydrogen atom leaves its electrons behind and is transferred as a proton, or it would be transferred as a hydrogen ion. We've learned in structure of an atom, a proton is a positively charged ion, and hydrogen ions are always proton donors. So the molecule that loses the proton is now a hydroxide ion. Take note, OH negative is the symbol. Now, when the molecule has an extra proton, it is now termed a hydronium ion, H3O+. It can also be represented or denoted as H+. So hydronium ions or hydrogen ions, but the hydronium has an extra proton, an extra hydrogen. So what then is water? Water, let's look at the chemical equation for water. Water is always going to split or dissociate into hydrogen ions and hydroxide ions, OH negative. H plus hydrogen ions, OH negative hydroxide ions. So I want you to make the association between hydrogen ions and hydroxide ions. So when you write down the equation, H2O, the chemical reaction splits into hydrogen ions and hydroxide ions. Below hydrogen ion, you're going to put acids. Below hydroxide ion, you're going to write down base. So the moment you see the term hydrogen ion, always related to acids, hydroxide ions to bases. So when you add any solutes to the hydrogen ions, which are the acids, or to the hydroxide ions, which are the bases, it will modify the concentration of that acid or base, of the hydrogen ions or hydroxide ions. And biologists, we use what we call the pH scale to describe whether a substance is an acid or a base, or whether the substance is acidic or basic. So let's define the term acids and bases. What is an acid? It is a substance that is going to increase the hydrogen ion concentration when it comes in contact with water or of a solution. I'm going to give you classic examples of acids and bases as I show you the pH scale in the next slide. What then is a base? A base is a substance, I like to say, that produces hydroxide ions in a solution, or when it comes in contact with water. Or another way to phrase it, it's going to reduce the hydrogen ion concentration of that solution. Strong acids and bases are going to completely dissociate, split, or break down in water. And we can see the weak acids and the bases, they reversibly are going to either release or accept back hydrogen ions. But they can still shift the balance of the hydrogen ions and hydroxide ions away from the neutral range, which is the pH is equal to 7. We're going to see that again on this pH scale, a little lower. So in any aqueous solution at 25 degrees Celsius, the product of the hydrogen ions and the hydroxide is constant. And therefore, concentration of hydrogen ions and hydroxide ions is equal to 10 to the power of minus 14. Why? Because the pH scale measures a range between 0 to 14. And it's measuring how acidic or basic a substance is on the scale. So how then do we define what then is the pH of a solution? It's defined by the negative logarithm of the hydrogen ion concentration. So pH is negative log into parentheses H plus hydrogen ion concentration. For a neutral solution, so for negative log, you're going to put negative 7 because it's the neutral range. Negative times negative is positive because neutral aqueous solution is 10 to the power of negative 7, the neutral range. And that's how you get pH is equal to 7 for a neutral solution. So acidic solutions, they have values less than 7. So on the pH scale, it goes from 0 to 7. Basic solutions, 7 to 14. And most of the biological fluids have a range between 6 to 8 on the pH scale. Now, I like to be very accurate in the scale that I determine. So this is the pH scale. The pH scale ranges from 0 to 14. I like to say from 0 to 6.9 to be very accurate would be the acidic scale. 7 is neutral, and 7.1 to 14 would be the basic scale. Now, what does every unit or number on the scale determine? It determines, or it informs you that it increases 10 times. So it increases, you move 10, 20, 30, 40, 50, 60, etc. till 140 times in its concentration. So let's try to see what and understand the pH values of particular substances and which has a higher concentration and why. So we see some of the acids. pH 1 is battery acid. Gastric juice is the juice that is released in the stomach that aids in digestion. pH of lemon juice is also equivalent to pH is equal to 2, vinegar, wine, cola, 3, etc. And you see here pH 6 is urine. Now, pH 7 is the neutral range, correct? Let's take a classic example because these are some of the questions, analytical and critical thinking questions you will be asked in the exam. So if I posed a question to you, if the pH of lemon juice is 2 and the pH of urine is 6, which substance has a greater pH and why? So think for a second. I'm going to give you a clue sentence to remember to answer these questions in the exam. Smaller the number on the pH scale, greater is its concentration. Why? Because as you move away from 0 to the neutral value, the concentration of that substance, and in this case, the acid, is going to decrease. Therefore, pH 2 lemon juice will have a greater concentration than pH 6 urine, because urine is closer to neutral value. So neutral range is pH is equal to 7, water, human blood, and tears. But take note of the pH of blood, which I mentioned in chapter 1 when we talk characteristics, homeostasis. Very important, I told you, homeostasis for body temperature 98.6 and pH of blood is 7.4. So 7.4 you would think should come not in the neutral but in the basic, but it is considered neutral, 7.4. We cannot, it should not increase 0.1, 0.2, 0.3. It means that homeostatic mechanism is not functional with respect to blood. Blood is not being maintained neutral. That indicates to us that there is some infection. So some of the basic substances, so the basic range will be from 8 to 14 or 7.9 to 14. Seawater, milk of magnesia, milk, household ammonia, bleach, oven cleaners, all, also your detergents, your soaps, they all fall in the basic range. So we've seen the moment you see hydroxide ions, it is a base. The moment you see hydrogen ions, it's an acid. Okay, so let's go with what is a buffer. Buffers are substances that minimize, they bring about small changes in the concentrations of hydrogen ions or hydroxide ions in a solution. Therefore, the buffer is going to maintain the internal environment in all living cells close to 7, which is the neutral range. Now, most buffer solutions, they consist of a weak acid and a weak base, which combine reversibly with hydrogen ions. So I want to give you a classic example of I call it the best human blood buffer system is, and I'm going to go to this slide here, which is called carbonic acid and bicarbonate ions. So I'm going to show you how carbonic acid and bicarbonate ions is formed in our body. So we have the words carbonic acid here, but the chemical formula is not here. I'll come back to this slide after explaining how carbonic acid is formed. So for example, I drank a lot of coffee this morning. So what is the level that is high in my body? Is the acid level high in my body or base? It has to be acid. If you drank a lot of orange juice, tomato juice, any acid, pineapple juice, citric acid, these are all acids, lemon juice, citric acid, orange juice. The level of acid is here, base level is here. What do we need to maintain at all times? Equilibrium. So how is this equilibrium going to be maintained in our body? This human blood buffer system is going to now either release hydrogen ions or absorb. So my acid level is here, base level is here. What can I do? What is a neutral substance? So to neutralize and bring it to equilibrium, I can either drink water, consume water, or I could drink a basic substance called milk. So watch what I'm doing. I'm inhaling. So I'm taking in air. Air is a mixture of gases. I would like if I only took in oxygen, but I'm getting in CO2 gas. So our body's composition is, our cells in the body are surrounded by 80 to 95% water. So the carbon dioxide that I am inhaling is going to now combine with the water that surrounds my cells. So CO2 combines with water, and now what is formed? So you have H2, you have 1C, and you have 2 plus 1, 3. H2CO3 is now called carbonic acid. So carbonic acid is part of the one buffer system in humans. So now let's take the other example. So my carbonic acid was high because I drank a lot of acids. How do I lower down and equilibrate with the base to form the neutral, to maintain neutral pH of 7? That carbonic acid now, because there's a high level of acid, that carbonic acid is now going to split. It's going to break down. When H2CO3 splits up in the chemical reaction, hydrogen ions. So this H2 is going to split, break down, hydrogen ions, one hydrogen is released, and one hydrogen combines with carbonate. Carbonate is a salt. Whenever you hear or see the suffix ATE, it indicates to you that it is a salt, carbonate, phosphate, nitrate, sulfate, ATE, they are all salts. So you have hydrogen ions plus bicarbonate, because when one hydrogen attaches to the salt, it forms bicarbonate ions. So now let's look at this scenario. If you drank a lot of milk or bases, the base level is high in your body. What should now the base do? So that bicarbonate ion has to now, it's going to reverse. It's going to now absorb all the hydrogen ions and it will form carbonic acid. So that's how the buffer system is functioning in human beings, to create that equilibrium and maintain a pH of 7, which is neutral. Now, this is what we call acidification in oceans. Acidification is a threat to our oceans. How do the levels of acids increase in the environment? It is on account of burning of fossil fuels. Human activities such as burning of fossil fuels are threatening the quality of water. Why? Because carbon dioxide gas is the main product of fossil fuel combustion. Combustion is burning. And 25% of all the CO2 that is being absorbed by the ocean is being generated by humans. And that CO2 we saw how it is going to form when it reacts with water, carbonic acid. So here in the oceans, you have the tropical fish. What are fish doing? Like you and me, they're respiring, but they are releasing the carbon dioxide gas. So the CO2 gas, the acid levels are increasing in the environment. You're seeing a plane flying, burning of fuel, which is being released, the CO2 gas, thereby increasing the acidification in the environment. And so we want to reduce ocean acidification. We want to stop burning fossil fuels. So as the seawater acidifies, hydrogen ions we saw combine with the carbonate to produce bicarbonate. Now, carbonate, which is the salt, is required for calcification. Calcify means to harden because of the production of calcium carbonate. You see, your nails are hard when you eat a lot of calcium. You have hard, your nails are nice and hard. Those individuals whose nails are brittle and break easily. You lack calcium. And so calcium carbonate is being produced in many marine organisms like the corals. If you go to a beach and you look at the rocks, sometimes you see small little white shells adhering to the substratum, to the hard surface of the rock. Those are called diatoms, diatoms, diatoms. And you try to pull out the shells. No, you cannot remove the shells. The diatoms cannot be removed. Why? It's very difficult because they are calcified, they are hardened with calcium carbonate. And so we human beings need to create this balance in the oceans, the lakes and rivers. How can we create this chemical balance? By preventing ourselves from burning tons of fossil fuels, eliminating CO2 gas into the environment and thereby into the oceans. So let's look at the graph here. In the scientific investigation lab on Saturday, I pointed out to you, a graph will have two axes, an x-axis and a y-axis. What goes on the x-axis is always the independent variable. What is plotted on the y-axis is always the dependent variable. So here we see carbonate, micromolecules of kilograms, molecules per kg of seawater versus the calcification rate in millimoles of calcium carbonate per meter square per day. So what type of a graph is this? This is a line graph. So what do we see here? This graph is indicating the effect of calcium carbonate saturation state on the calcification rate of experimental coral reef. So as the micromoles per kilograms of seawater, the carbonate levels increase, you're seeing the increments, and on the x-axis, you see an increment of 10 to 20 to 30, 40, 50, 60. So also the calcification rate is going to increase. Now, I don't know if you're familiar, but you will be plotting when we graphs, line graphs, best fit graphs. What are best fit graphs? Where you're going to take those points that come within, you're going to draw your line to the points that exactly pass through the line. So these points are not passing to the line. So you will eliminate those points. You won't plot the graph using those points. And I will go into detail and show you exactly how to plot a best line graph. Okay. And this is just to reiterate what acids donate the hydrogen ions in aqueous solution. Aqueous is water, and bases are going to donate hydroxide ions. Students, I encourage you, go through these video recordings and the slides at your own leisure and start preparing for the exam. Take care, students. I hope to see you in the lab. Bye-bye. Najma, 1 minute. Najma. You can unmute. You unmute. Ah, yeah. So what you thought, Najma?